Hello, this is an extensive multi-hour course on work orchestration for agentic engineering. We'll be looking at different ways of orchestrating work across different agent harnesses, and then we'll focus specifically on a new system called Symphony, designed by OpenAI. This is broken up into 4 different sections. The first section covers the foundations of agentic work orchestration, where we will talk about core challenges, including scope, context, and execution. We'll look at operational definitions, including the agent harness, orchestration, subagent, context engineering, work orchestration. And we will go over shared principles of autonomy.
Welcome to this lesson. Today we are diving into the core challenges of agentic engineering. We will explore why 3 specific long-horizon problems matter so much to your success. First, we will look at scope and how to keep an agent's work perfectly bounded and focused. Next, we will dive into context, learning how to preserve vital operational memory. Then we will tackle execution, discovering how to turn your plans into reliable action. After that, we will see exactly why these 3 challenges are deeply connected and how they are shared across the entire orchestration landscape, no matter what tools you use. Finally, we will wrap up with a key takeaway you can apply immediately. Mastering these 3 pillars will completely transform how you build and manage intelligent agents. So let us jump right in and get started. It is easy to be blown away by a quick demo of an AI agent, but in real-world software engineering, those impressive single-session demos often fall apart. Why? Because long-horizon tasks, the kind that take time and multiple steps to complete, create intense pressures that simple chat interactions just are not built to handle. Let's break down what actually happens. First, a real engineering task is usually too massive to be processed as one single coherent thought process. As the agent works, the session inevitably drags on, slowly accumulating irrelevant noise, while losing track of crucial details from earlier steps. Then there is the execution gap. An agent's reasoning might sound perfectly logical, but when it actually tries to run the code or deploy the fix, it fails. Real engineering work is messy. It requires retrees, branching out to test new ideas, validating results, and sometimes handing off tasks to other specialized tools. And when things truly get stuck, human operators need a seamless way to step in and guide the process without having to micromanage every single keystroke. This reality is driving a massive shift in how we build these systems. Agentic engineering is no longer just about writing the perfect prompt. Today, the focus is increasingly on orchestration. The true challenge we face is no longer simply how to get a good answer from a model, it is how to reliably keep complex, multi-step work on track over time. Let's talk about scope, and specifically the importance of keeping an agent's work bounded. What exactly do we mean by scope in this context? Simply put, it is the challenge of defining exactly what an AI agent is trying to accomplish, how much it is allowed to take on at any given time, and what actually counts as successful progress. When we give an agent a scope that is too broad, it tends to drift. The agent might attempt to make too many changes at once, chase after unintended goals, or completely lose track of its original priorities. If you are applying this to software engineering, you might see this manifest as massive, oversized code modifications, speculative rewrites of things that did not need fixing, or endless loops where the agent makes partial progress but never quite finishes the job. So, what does a failure of scope actually look like in practice? There are a few common red flags. An agent might try to solve a massive problem in a single pass. It might start tweaking entirely unrelated parts of a code base. It could forget its actual objective halfway through, or treat a highly complex project as one giant unwieldy task instead of breaking it down into manageable pieces. You might also see it repeatedly expanding the scope of its work rather than simply finishing the task at hand. This is exactly why long-horizon autonomy almost always requires us to put strict boundaries around tasks. How do we actually manage this? Different orchestration systems use different mechanisms, but the patterns will probably sound familiar to anyone who has managed human teams. We use PRDs and specifications. We create phase-based plans or break the work down into smaller stories, subtasks, and isolated tickets. Sometimes we restrict the agent to per-task workspaces or work trees, or we use specialized subagents focused on very narrow goals. The underlying philosophy here is simple. An agent should not have to carry the weight of an entire problem as one massive, undifferentiated block. It needs to work on smaller, clearly defined units. But it is important to remember that scoping is not just about breaking tasks down. Decomposition is a big part of it, but scope is much broader than that. It also dictates priorities, sets clear stopping conditions, and defines who owns a particular subtask. It establishes hard boundaries around which files or systems an agent is actually allowed to touch, and it provides clarity on what needs to be done right now versus what belongs in a later iteration. Ultimately, a well-scoped system strikes a careful balance. It gives the agent enough room to do its work, but not so much room that it loses the thread completely. Let's talk about context. When we build and work with AI agents, context is essentially the informational environment the agent receives while it works. For quick tasks, a standard chat window is usually enough. But in long horizon engineering tasks, relying purely on an ephemeral conversational window becomes a major liability. Think about everything an agent needs to remember over the course of a long project. It needs to track current goals, prior decisions, and repository conventions. It has to keep implementation plans, test expectations, and research findings top of mind, not to mention remembering the work it has already completed and the specific errors it encountered in previous iterations. If all that crucial knowledge lives only in a live, ongoing session, the entire system becomes highly fragile. If you start a fresh session, that memory is completely lost. If a session gets too long, the AI might compress the information poorly. And in a noisy session, important details simply get buried. As work continues, the session naturally accumulates clutter. You get raw tool outputs, partial attempts, repeated instructions, stale intermediate reasoning, and a whole host of irrelevant details. This leads to a phenomenon known as context rot. Context rot is the degradation of useful context as the session fills up with noise, drift, compression artifacts, and a general loss of focus. The core problem here is not just about hitting a token limit, it is about a steep drop in informational quality. So how do modern agentic systems solve this? They externalize critical memory. Instead of relying on a single chat window, they store information in persistent ways. This includes using specialized skills, persistent memory files, and detailed plans or state documents. It also involves relying on repository-level guidance documents such as agents.md, Claude.md, project.md, or roadmap.md. Other solutions involve integrating issue trackers, research documents, summaries, the project's Git history, and persistent ledgers or conversational threads. The important shift in thinking is this: good systems do not treat context as whatever happens to still be sitting inside the chat history. Instead, they actively design the informational environment. This brings us to a vital discipline known as context engineering. Context engineering means actively deciding exactly what the agent should know at each specific step. It involves choosing what data to inject into the prompt and what to leave out. It requires summarizing prior work, structuring repository knowledge clearly, selecting the right tools, and preserving the state of the project entirely outside the immediate session. Ultimately, without context engineering, long-running work becomes fundamentally unreliable, no matter how powerful the underlying AI model happens to be. Now let's talk about execution, which is the process of turning our plans into reliable action. At its core, execution is the challenge of getting work actually carried out in an environment in a way that is automated, verifiable, and safe. You can think of execution as being much more than just running a simple command. In engineering work, executing a task might involve editing files, running terminal commands, or kicking off builds and tests. It can also include type checks, browser verification, waiting for continuous integration feedback, handling reviews and retries, or even calling out to subagents and external systems. Because this process is so complex, reasoning alone just is not enough. The system needs a reliable control loop that can verify whether the work it attempted actually succeeded. You might wonder why execution is treated as a completely separate problem from reasoning. The reality is that an AI model can propose a completely plausible next step, but still fail operationally. For example, the suggested command might be wrong, or a perfectly logical file change might accidentally break the build. The tests might fail, the environment might reject the action, or the agent might simply misunderstand the result of what it just did. This is why orchestration is not just about generating actions. It is really about closing the loop between the action taken and the feedback received. This brings us to one of the strongest common principles across orchestration systems. Verification matters at least as much as generation. When we talk about typical verification mechanisms, we mean things like automated tests, type checking, and linting. We also rely on CI feedback, browser verification, structured error reporting, and reviews, whether that review is done by a human or by another AI agent. A system that can generate changes but cannot reliably verify them is not robust. It is only fast at producing untrusted output. Finally, execution naturally raises serious questions about safety and control. In practical, real-world systems, we ensure safe execution through sandboxing, strict permission controls, and mandatory approval steps. We use isolated workspaces, severely limit credentials, and draw crystal clear boundaries around exactly which systems can be touched. Ultimately, the goal of execution is not just to act. The goal is to act with total legibility and control. Scope, context, and execution are not isolated challenges. They are deeply entangled, constantly feeding into and influencing one another. Let's start with how scope affects context. A badly scoped task essentially creates a noisy environment. If you have too many goals, too many files, or competing priorities active all at once, the informational context becomes chaotic and much harder for an AI agent to manage. This directly leads into our next point. Context affects execution. poor context inevitably leads to bad action. If the agent lacks the correct repository conventions, the history of the task, or clear expectations for validation, it simply will not execute reliably. And finally, execution loops right back around to affect both scope and context. Every action produces a new state. Successes, failures, code changes, test results, and review outcomes immediately become the new context for the next step. Beyond that, if you notice repeated execution failures, that is often a strong signal that your initial scope is still too broad and needs to be reined in. Because these three elements are so closely connected, modern orchestration systems revolve around a repeating cycle. First, you define or refine the scope. Second, you prepare the context. Third, you actually execute the work. Fourth, you verify the result. Fifth, you update the system state with what just happened. And sixth, you either continue the task or split it down even further. By moving through this continuous loop, we keep scope, context, and execution perfectly aligned and moving forward. An important takeaway here is that these three problems don't just belong to one specific category of system. They are shared across the entire orchestration landscape. You will find them in context-based orchestration inside a harness and in external execution loops. You will see them in persistent workspace managers, in programmatic integrations using SDKs or protocols, and even in larger work orchestration systems operating at the issue or ticket level. The core difference between all these approaches is really just a matter of how they manage scope, context, and execution, not whether they need to manage them. Every single one of them faces these challenges. To give you an idea of how they handle this differently, let's look at a few examples. Context-based systems often try to improve scope and execution by loading better skills, deeper memory, and stricter rules directly into the harness. External loops, meanwhile, focus on improving execution and keeping the context fresh by restarting work in carefully controlled iterations. If we look at persistent workspace managers, their main strategy is to preserve state and maintain continuity across multiple separate runs. And finally, broader work orchestration systems try to manage scope and execution from a much higher vantage point. They tackle these challenges at the operational level, managing things like individual tickets, workspaces, retries, reviews, and ultimately landing the changes. Let's bring it all together. If you really want to understand why modern agentic systems are evolving the way they are, it all boils down to one fundamental takeaway. As the field of AI advances, developers keep running into the exact same three persistent challenges: scope, context, and execution. Let's break those down. The first is scope. For an agent to be useful, its work must stay bounded and clearly legible. We need to understand exactly what the system is trying to accomplish without it going off track. The second challenge is context. When an agent is working on a complex, ongoing task, critical information has to survive beyond a single brief session. The system needs to carry forward what it has already learned and what it still needs to do. And the third challenge is execution. Any action an agent takes must be verifiable, strictly controlled, and above all, safe. Keep those three pillars in mind, because everything else we cover in this course builds directly on that foundation. As we explore different frameworks, developer tools, and orchestration systems later on, you'll notice a running theme. While they might package their solutions in very different ways, they are all ultimately trying to govern those exact same three dimensions of long-horizon autonomous work. Welcome to our lesson on operational definitions in agentic engineering. Before we dive into comparing complex AI systems, it's crucial that we all speak the exact same language. In this visual overview, we'll break down the 5 core terms you'll use throughout this course: the agent harness, orchestration, subagents, context engineering, and work orchestration. Once we have those down, we'll explore exactly how these definitions connect to form a complete functioning ecosystem and wrap up with an essential key takeaway. It is incredibly easy to get lost in the buzzwords of this field, but mastering these precise concepts will give you the clarity and confidence you need to effectively design powerful, high-level AI workflows. Let's get started. Let's explore the concept of an agent harness. When we think about AI agents, it is easy to focus entirely on the underlying model. However, an agent harness is the vital operational layer that wraps around one or more of these models, giving them the concrete capabilities needed for actual engineering work. You can think of the harness not just as the brain of the operation, but as the complete work environment for the agent. What exactly does this environment include? A robust harness equips the model with a wide variety of practical capabilities. It provides the tools an agent needs to take action, such as file editing, terminal access, and system navigation. It also establishes important boundaries by managing permissions and approval workflows. Beyond that, a harness handles the agent's operational memory, maintains sessions, and controls context so the agent doesn't lose its train of thought. It can also run validation mechanisms to ensure work is correct, and even manage system hooks or coordinate with other subagents. In short, the harness is the bridge that turns a basic language model into a functional entity capable of participating in real-world engineering tasks. Why does understanding the harness matter so much? Because 2 different AI systems can be powered by the exact same underlying model, yet behave in entirely different ways. This is all due to how their harnesses are built. For example, one harness might feature highly robust file operations, strict approval controls, and excellent context management. Another harness using that same model might suffer from weak memory handling or have a very limited ability to execute commands. Because of this, when people debate and compare different coding agents, they are very often comparing the design of the harness, rather than just the raw intelligence or quality of the AI model. Let's move on to our second major concept, orchestration. In simple terms, orchestration means coordinating the workflow of a single harness or multiple harnesses working together. The goal here is to enable the system to carry complex tasks all the way through to completion, requiring significantly less human micromanagement. How does this coordination actually happen? It can occur at several different levels. First, it can happen directly inside the harness. This is the most local form of orchestration, where the harness itself helps shape how work gets done. It does this through internal tools like specific skills, plugins, initial prompts, custom commands, or persistent rules. Stepping one level out, coordination can also happen outside the harness. In this scenario, the harness becomes just one component inside a larger control loop. This external coordination is usually managed through repetitive loops, external scripts, dedicated workspaces, queues, or specialized work managers. Moving further out, we have the programmatic integration layer. This is where a host system coordinates the harness, making it a functional part of a much larger application architecture. This type of coordination relies on software development kits, network protocols, embeddable servers, or specialized tool interfaces. Finally, at an even higher level, orchestration can be driven from a work management layer. Think of the tools teams use every day, like issue trackers, automated workflow systems, ticket queues, or overarching project management platforms. At this level, a fundamental shift happens for the human operator. Instead of managing individual prompts or chat sessions, you start managing broader units of work. So why does all of this matter? One of the core takeaways of this course is understanding that orchestration does not live in just one place. It is highly flexible. It can happen locally inside the harness, structurally outside of it, programmatically through code, or from the very top through a high-level work system. Let's talk about subagents. A subagent is essentially a specialized unit of execution that receives delegated tasks from the main system. A subagent can actually take a few different forms. It might be an additional session running on the same harness, a completely different model, a specific tool, or even a programmatic call out to an external agent. But regardless of the form it takes, the driving idea is always specialization and delegation. So what makes subagents so useful? Primarily, they help us break complex work into narrower, manageable units. Instead of relying on one general session to do absolutely everything, the system can assign specific responsibilities to different execution units. For example, you could have one subagent dedicated solely to analyzing requirements, while another inspects a codebase. You might use different subagents to implement a focused change, run verification tests, summarize findings, or even critique the output of another agent. This approach is critical for managing the long horizon problems we tackle throughout this course. First, subagents help manage scope by strictly narrowing what each individual unit is responsible for. Second, they improve execution by creating work loops that are highly focused and easier to verify. And third, they help manage context. By delegating tasks, each unit can operate using only the highly targeted information it actually needs, rather than being overwhelmed by the entire project. Keep in mind, a subagent does not need to be a fully autonomous persona. Ultimately, it is simply a delegated execution unit designed to take on a narrower job and do it well. Let's move on to a concept known as context engineering. You've probably heard of prompt engineering, which is all about writing the perfect instructions for an AI. Context engineering goes much deeper. It is the design of the entire informational environment that an AI agent receives. It is not just about crafting a clever sentence. Context engineering encompasses all the vital information structures that shape how an agent behaves. This includes managing persistent memory, state files, and the specific skills an agent can use. It involves providing background research, active plans, summaries of past actions, coding conventions, and carefully selecting which tools are available at any given moment. Ultimately, it is about having precise control over exactly what information gets fed to the agent at every single step of a process. Because of this, context engineering has become one of the absolute core disciplines of building effective AI agents. Why does this matter so much? Because even the most advanced, powerful AI model will fail if its informational environment is poor. If an agent loads the wrong files, if it is missing the overall project plan, if it cannot see the rules of your repository, or if old stale information is overwhelming the current task, the agent will simply make bad decisions. Good context engineering addresses these risks by asking a series of strategic questions. What exactly should the agent know right now? What information needs to be remembered across different sessions? What details should be summarized? And equally important, what should be omitted completely? It also asks which tools should be available for the current step, and which specific project artifacts need to be present to guide the agent's behavior. As you build more complex systems, you need to shift your mindset from prompt engineering to context engineering. While prompt engineering focuses on wording a message well, context engineering is much broader. It treats the agent's informational environment as a structural system design problem rather than just a phrasing problem. Making this shift in your thinking is absolutely essential if you want to build agents capable of successfully completing long, complex, and autonomous work. Now let's explore work orchestration. This operates at a much higher layer than the orchestration of a single session. Instead of just coordinating a single prompt or one AI agent, work orchestration manages the entire lifecycle of a task as a complete operational unit. So what exactly does this higher layer manage? As the center of gravity moves away from a simple interactive chat and toward structured work management, this layer takes on a lot of heavy lifting. It manages support tickets, per-issue workspaces, and code branches. It handles retries when things fail, maintains state across interactions, and coordinates automated tests, peer reviews, and the final landing of changes into production. Why is this distinction so important? Well, a single AI agent session might be great for helping you complete a quick, isolated task. But real-world, long-horizon engineering work demands much more than a good chat session. It requires persistent state, retry logic, and workspace isolation. It needs rigorous validation, formal review, issue-level tracking, and smooth transitions from one workflow stage to the next. All of that complex, ongoing coordination is exactly the territory of work orchestration. For you, the human operator, this introduces a practical and fundamental shift in how you work. At this orchestration level, you are no longer sitting there mainly guiding prompts turn by turn. Instead, your role elevates. You are increasingly managing overarching tasks, tickets, and system policies. You're overseeing workflows, handling reviews, and stepping in to manage exceptions. This evolution from an interactive prompter to a strategic workflow manager is one of the major defining shifts we are exploring in this course. Now that we have looked at these terms individually, let's explore how they all connect. While they are closely related, they actually refer to completely different layers of the system. Let's build this picture layer by layer. First, we have the agent harness. You can think of this as the foundational workspace. It is the operational environment where the agent actually does its work. Next is context engineering. If the harness is the workspace, context engineering provides the instructions and background material. It is the careful design of the informational environment that shapes the agent's behavior and dictates exactly what it knows. Inside this broader workflow, you will often find subagents. These are specialized, delegated execution units. They help divide and specialize the execution, taking on specific parts of the task so the main system can operate efficiently. With all these moving parts, we need orchestration. Orchestration acts as a workflow coordinator across one or more harnesses, making sure the immediate steps happen in the right order and that the work proceeds smoothly. Finally, we step back to look at work orchestration. This is the highest level of coordination. Instead of just focusing on a single task, work orchestration manages complete units of work over a longer period of time. It oversees the entire lifecycle of the work, well above any single session. To put it simply, the harness provides the environment. Context engineering shapes what the agent knows. Subagents divide and specialize the execution. Orchestration coordinates how the immediate work proceeds. And work orchestration manages the big picture lifecycle of the work. Let's bring all of this together with a key takeaway. The definitions we have just covered are more than just abstract concepts. They provide the essential vocabulary we will be using for the rest of this course. But importantly, they also point to a much broader fundamental shift happening in the field right now. We are seeing a move away from purely model-centric thinking, where all the focus is on the AI itself, toward harness-centric thinking, where the systems surrounding and supporting the AI are just as crucial. We are moving past single, isolated prompts and advancing toward deeply engineered context. Instead of sitting through single back-and-forth chat sessions, we are shifting toward delegated execution, where we hand off complex tasks for the system to handle autonomously. And finally, we are evolving from simple local coordination to comprehensive work-level orchestration. Why does all of this matter? Because once these core definitions are clear in your mind, the massive, often confusing landscape of AI tools becomes infinitely easier to analyze. As we move forward, you will be able to look at any new system and ask the right questions. You will be able to see exactly where the orchestration lives, understand how the tool manages context, evaluate how it delegates tasks to subagents, and determine whether it stops at basic session control or scales all the way up to full work orchestration. Welcome! Today we are exploring the shared principles of autonomy in agentic engineering. While the landscape of agent tools might look vastly different in architecture and style, they all converge on a few core practical lessons. In this lesson, we will break down 5 essential principles: externalizing useful context, decomposing work, the need for specialization, why verification matters just as much as generation, and why repository legibility is an absolute must. After that, we will explore exactly how all of these principles work together and wrap up with a powerful key takeaway. Mastering these foundational concepts will completely transform how you design and build autonomous systems. Let's dive in. Let's dive into one of the most important lessons in agentic engineering. Useful context must be externalized. When building autonomous systems, it is incredibly tempting to rely on an accumulated conversation to keep the agent on track. But for long-running work, this approach is fundamentally flawed. You need a memory system that survives beyond a single session. Your agent must be able to recover the important state of its work without depending on the fragile thread of conversational continuity. So, what exactly counts as useful context? The key idea is that important knowledge must be made available in an explicit, easily retrievable form, rather than buried in a chat log. This context can live in many places. It might take the form of state files, research notes, or structured project plans. It could be stored in dedicated workspaces, system logs, or ticketing systems. It even includes external resources like Git commit histories, repository guidance files, specific agent skills, or written summaries of prior iterations. Externalizing this information is crucial, and here is why. Long horizon work is rarely completed in one straight shot. It spans multiple iterations, retrees, and entirely different sessions. It often involves handoffs between specialized subagents or pauses for human review. If all the critical context lives only inside one continuous session, your system becomes brittle. Start a fresh session, and the agent completely loses the thread. Keep a session running too long, and it accumulates confusing noise. Worse, operators end up having to re-explain the exact same facts repeatedly. To solve this, we need to treat externalization as a fundamental design habit. Strong, autonomous systems treat context as something to actively engineer, preserve, and update deliberately. They create concrete artifacts that carry the most important parts of the work forward. These artifacts record exactly what the task is, what approaches have already been tried, what constraints matter, what decisions have been made, and what the next step should be. Ultimately, this is why context engineering is central to true autonomy. Building effective agents is not just a matter of writing smarter prompts. It is about building an explicit, reliable informational environment that the system can actually navigate and use. Let's move on to our second major principle. Work must be decomposed. Put simply, an agent's autonomy drastically improves when its work is divided into small, verifiable units. Think about what happens when you give an AI agent a large, ambiguous objective. It becomes incredibly difficult for that agent to execute reliably over a long period. As the scope of a task expands, the agent struggles to maintain focus. The quality of its context starts to degrade, and it becomes much harder to verify if real, tangible progress is actually being made. To fix this, we have to break the work down. Now, what this decomposition looks like will vary depending on the system you are using. You might break work into individual tasks, user stories, or project phases. You might use subtasks, discrete issues, or stepwise plans. In some setups, this means creating separate workspaces or making specialized calls to dedicated sub-agents. The exact mechanism varies, but the core principle remains exactly the same. The agent needs to work on bounded units that are easy to complete and easy to verify. But why do these smaller units help so much? First, they significantly reduce the context burden on the agent. They also make the scope of the work crystal clear and create obvious stopping conditions. Smaller units make it much simpler to verify that a job was done correctly. Plus, if a mistake does happen, you can retry or correct that specific unit without having to restart the entire project from scratch. Finally, smaller discrete pieces of work make it much easier to hand tasks back and forth, whether that's between different AI agents or between a human and an agent. It is also important to realize that decomposition isn't just about planning. It is a vital control strategy. Breaking work down helps the overall system avoid long, uncontrolled chains of decisions, instead of forcing a single agent session to juggle an entire massive project as one giant mental object. The system transforms the project into a sequence of manageable, bite-sized work items. This is a foundational concept, and it is a principle you will see everywhere in modern AI orchestration, from context-based workflows to issue-driven work systems. Let's move on to our third key principle. Specialization must exist. When we look at long-horizon autonomous work, one thing becomes very clear, and that is that specialization is a massive advantage. Over and over again, the field keeps rediscovering the exact same pattern. Systems simply become more reliable when you don't ask every single unit to do absolutely everything. This specialization can take many different forms. It might look like distinct skills, dedicated subagents, or even entirely different AI models working together. You might use parallel workers, role-based agents, separate verification agents, or simply specific tools that are highly tailored to narrow jobs. But why does this help so much? Specialization improves overall autonomy in a few critical ways. First, it narrows the scope of a task, which naturally reduces context overload. It also makes expectations much clearer, increases the repeatability of the process, and almost always improves the final quality of the execution. Think about it practically. In a complex workflow, you might have one unit that is perfectly suited for high-level planning, while others handle the actual implementation, code review, or background research. You might delegate summarization, test writing, or browser verification to entirely different units, letting each excel at what it does best. Now, there's a common misconception here. We need to be clear that specialization does not require you to build a giant, elaborate, multi-agent society. Your system doesn't need all that theatrical agent drama to reap the benefits. Often, specialization is incredibly lightweight. It could just be a named skill inside your system's harness, a quick verification subagent, or using a specific, smaller model for a narrower task. It might even be as simple as spinning up a separate session with a much tighter brief, or invoking a dedicated tool. The core point here is operational, not theatrical. By giving different parts of your workflow narrower, clearly defined responsibilities, the entire system becomes dramatically more robust and capable. Let's explore a foundational principle shared across modern AI orchestration systems. Verification matters just as much as generation. Think about the current landscape of artificial intelligence. It has become incredibly easy to get agents to produce code, write plans, generate summaries, and make edits. The generation part is fast and accessible, but the much harder problem is establishing whether that generated output is actually correct enough to trust. This is where verification comes in, and its primary job is to close the control loop. True autonomy requires much more than just producing an action. An autonomous system must be able to evaluate the result of its action and use that information to decide what to do next. Because of this, orchestration systems rely heavily on various forms of verification. Depending on the task, this might involve running automated tests, type checking, or linting. It might mean relying on continuous integration feedback, browser verification, or even having a separate AI agent review the work. It also includes handling structured execution errors, or, when the stakes are high, pausing the system to get human approval. But why is this so central to how these systems work? Without strong verification, an AI system is essentially flying blind. It has no reliable way to distinguish between real progress and a failure that just happens to look plausible. Without these checks, an agent might easily introduce regressions or achieve a superficial success that quietly breaks something else in the background. Verification is the crucial step that turns a stream of unaudited, hopeful guesses into a controlled and reliable execution process. Ultimately, generation and verification belong together. In mature agentic systems, they form a continuous loop. First, the agent proposes or implements a change. Second, the system verifies it. Third, the agent inspects the result of that verification. Fourth, the system updates its context and state. And finally, based on that feedback, the agent decides whether to continue forward, retry the action, or revise its entire approach. This continuous loop of generating, checking, and adapting is what sets simple automation apart from true autonomy. In fact, it is one of the clearest markers of a serious, robust orchestration system. Let's move on to our fifth principle. Repository legibility is a condition for autonomy. Simply put, if you want sustained, autonomous work from an AI agent inside a codebase, that repository must become an agent-legible environment. It is incredibly easy to underestimate this principle. Think about how human developers navigate a codebase. We rely heavily on informal cues, tribal knowledge, and a general familiarity that we build up over time. AI agents don't operate that way. They require a much clearer, more explicit structure. So what exactly does an agent-legible repository look like? It emphasizes a few key ingredients. First, it requires clear conventions and persistent memory. It relies on explicit file contracts, distinctly named skills or commands, and a very clear representation of both the plan and the current state. When these features are baked into the environment, it becomes much easier for agents to orient themselves and pick up right where they left off, maintaining consistency across multiple sessions. The reason this matters is that agents simply work better when their environment makes the workflow entirely visible. The repository should clearly communicate where plans live and where state is recorded. It should map out how files relate to each other, which commands are relevant, what rules govern changes, and how progress is represented. In a messy or disorganized repository, an agent has to burn a lot of effort just trying to rediscover the structure. But in a highly legible repository, all of that effort goes directly towards solving the actual task. This represents a major shift in perspective. We have to stop thinking of the repository as just a passive piece of input that we feed to an agent. Instead, repository design becomes an active part of autonomy design. The environment itself acts as a part of the control system. When a repository is built to be easily navigated and interpreted by an agent, it supports cleaner context injection and much safer execution. It ensures stronger continuity, smoother handoffs, and highly reliable verification. And that is exactly why making your repository legible isn't just a matter of developer ergonomics. It is a foundational principle of shared autonomy. We have explored the 5 core principles, but it is important to understand that they do not operate in a vacuum. Instead, they actively reinforce one another, creating a powerful, self-sustaining cycle. Let us walk through how they connect. First, externalized context directly supports decomposition. When your plans, current state, and prior work are safely persisted outside the agent's immediate memory, the system does not have to juggle everything at once. This allows you to divide the overall workload much more cleanly, and it ensures that if a process stops, it can resume highly reliably. Once you have decomposed a large task into smaller work units, specialization naturally follows. Having bite-sized tasks makes it incredibly easy to assign very focused responsibilities to specific skills, dedicated sub-agents, or separate work sessions. That specialization is exactly what makes verification so effective. When you pair a narrowly focused worker with a narrowly focused reviewer, each of them can do their specific job with remarkable reliability. This is far more effective than relying on a single general-purpose agent trying to improvise the entire process from start to finish. But to verify anything effectively, your verification process depends heavily on a legible environment. Things like automated tests, well-defined plans, clear file contracts, and consistent repository conventions are what actually make the agent's results easy to evaluate in the first place. Finally, this brings us full circle because repository legibility directly strengthens the quality of your externalized context. A clean, highly organized environment makes it incredibly easy for the system to find and inject exactly the right information at exactly the right time. Because these principles continuously feed into and strengthen one another, they create a highly robust system. This interconnectedness is exactly why the field of artificial intelligence engineering keeps converging on these same 5 principles, regardless of the specific orchestration style being used. Let's wrap up with our key takeaways. Throughout this course, we've explored several foundational systems. You've likely noticed that the coordinating brain of these systems can live in quite a few different places. It might be housed inside a testing harness or run in an external loop. It could be managed by a persistent workspace manager embedded into a host application via an SDK, or even operate across a broader work system using tickets and workspaces. But despite these structural differences, all of these systems ultimately teach us the exact same operational lessons. First, useful context must be externalized so the system can access it reliably. Second, complex work has to be decomposed into smaller manageable steps. Third, specialization is essential for efficiency. Fourth, verifying the work matters just as much as generating it. And fifth, repository legibility is a non-negotiable condition for autonomy. An AI simply cannot operate independently if it cannot clearly read and navigate its environment. These 5 principles give us a practical baseline for understanding autonomy. They explain why some systems can successfully scale far beyond basic demos, while others completely collapse under the weight of long-horizon work. Keep these principles fresh in your mind. They prepare the ground perfectly for our next lessons, where we will explore how these foundational ideas are expressed through different orchestration architectures.